Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I hope you are all fine and enjoying best of your health. So in connection with the online lecture for the course of organic reaction mechanism, the today's lecture will be about the reactions that involve cleavage of carbon-carbon bond. So in this lecture we will consider the following concepts, that is, what do we mean by oxidative cleavage? Second, what do you mean by oxidative cleavage of alcohols? How can we carry out cleavage of alkenes, alkynes, and the ketones? So firstly, we will consider what do we mean by oxidative cleavage. Well, when certain type of compounds are treated with certain reagents, so as a result we break carbon-carbon bonds and we form new carbon-oxygen bonds, right? So it's important in the oxidative cleavage that we break the carbon-carbon bond, and carbon-oxygen bonds are also formed as well. So overall, the number of oxygen-carbon bonds are higher than the number of carbon-carbon bonds that have been broken. For example, if we break a single carbon-carbon bond and we form two carbon-oxygen bonds, so the net number of oxygen carbon bonds is higher. Since the number of oxygen carbon bond is higher, so we say that oxidative cleavage is a type of oxidation reaction, right? So what do we mean by oxidative cleavage? Oxidative cleavage is a way to break the carbon-carbon bonds, and as a result we form carbon-oxygen bonds, right? So oxidative cleavage, that's a mean to break a carbon-carbon bond, is actually a type of oxidation reactions. So in the first statement we said that certain type of compounds undergo oxidative cleavage. So which type of compounds undergo oxidative cleavage? So these compounds include 1,2-diols, which are also known as the vicinal diol, alkenes, alkynes, and certain ketones, right? No, not all type of ketones can undergo oxidative cleavage. So we'll see which type of ketones will undergo oxidative cleavage. So we will discuss all of these one by one in a sequential way. So firstly, we will consider the oxidative cleavage of alcohols. So when we say oxidative cleavage of alcohols, we are normally considering the alcohols that are in the form of diols, right? So what do we mean by diols? So diols are organic compounds in which we have an OH group on two adjacent carbons. So presence of two OH groups, two ols on adjacent carbon, so such compounds are called vicinal diols, right? So we cannot carry out cleavage of simple alcohols. So if you have monohydric alcohol, you cannot carry out the oxidative cleavage. However, if you want to carry out the oxidative cleavage, it is necessary that you have a diol or triol, whatever, but those diols should be vicinal. They should be on adjacent carbons, right? So when these vicinal diols are treated with sodium periodate, NaIO4, right? So when these diols are treated with sodium periodate, we break the carbon-carbon bond and we form two new carbon-oxygen bonds, right? So as a result of this cleavage, what we get is that we get two aldehydes or two ketones, or one aldehyde or one ketone. So what we get depends on how our diol is looking like, right? So the nature of the product, whether we get two aldehydes or we get two ketones or we get one aldehyde and ketone, it depends on the structure of our reactant diols. For example, so suppose, okay, so here is a mechanism as well, and we are considering the structure as well. So first, just see the nature of substituent on this diol. So this is a vicinal diol. You can see 2-hydroxy on the adjacent atoms, right? And here you can see that on one carbon we have a hydrogen, and on one carbon we have an R group, while the other carbon has R3 and R4 groups. So what happens that in this reaction we break this carbon-carbon bond from the center, right? And both of these fragments will become carbonyl compounds. So here this fragment, this carbonyl compound will have one H and one R1 group, so that will become an aldehyde, you can say that. And this other fragment, okay, so this will be carbon oxygen double bond, and there we will have a R3 group and an R4 group. So you can say that this carbon will form the ketonic group, right? So just by seeing the structure, we can predict what will be our product. So in this structure, in this diol, our product will be one aldehyde and a ketone, right? So how does the mechanism proceed? This is important thing. So in this mechanism, we are using sodium periodate, so NaIO4. The sodium is not participating in the reaction, it is just present in the reaction mixture. So since it's not participating in the reaction, we have not shown it here, right? Sodium is missing, but that's present in the reaction mixture, and since it doesn't take part in the reaction mixture, so we say that sodium is a spectator ion here. So the important thing is here the iodine. You say this central atom is iodine, and this iodine at present is in oxidation state of 7, right? So iodine is forming 7 bonds here, you can say that. So this iodine is in oxidation state of 7, right? So what happens that, so this oxygen of diol will attack on this pi-electronic system, right, of iodine oxygen bond. So iodine is highly electronically deficient because of presence of 4 oxygens with it, right? So what happens that this pi electron will shift towards this iodine, and what happens next that this pi electron will move towards this oxygen. So we are forming a 5-membered transition state here. And you can see there was the oxidation state of iodine here. So we have oxidation state of iodine is still 7. Right, so there is no change in state of iodine in the transition state. Right, so this is our intermediate. And further what happens that we get a rearrangement. So in this transition state, in this you may say reactive intermediate, in this intermediate, what happens that the bond between carbon and carbon is shifting, and this bond is going towards this carbon and oxygen. So we are forming a carbon oxygen double bond here, right? So as a result, what happens that next this bond will shift towards iodine, because oxygen is forming 3 bonds, which is not possible for it. So this bond between oxygen and iodine is being broken. Then this electron between oxygen and iodine, this is shifting towards again a carbon oxygen bond. So we are forming a double bond here. You can see that, right? So as a result, what we are getting this iodine. Now iodine is in oxidation state of 5. So there's a change in oxidation state of iodine. So previously the oxidation state of iodine was 7 in the reactant and in the intermediate as well. However, in the product now iodine has oxidation state of 5, right? So what happens that this iodine had 4 oxygen, you can simply take that. Now this iodine has 3 oxygens, so it has lost 1 oxygen, right? The loss of oxidation oxygen is called reduction. So here the iodine has been reduced, right? And now you can say that we had single carbon oxygen bonds in the reactant, but now we are having carbon oxygen double bonds. So our product has been oxidized. So iodine is here causing oxidation of our substrate of our reactant, but itself is getting reduced. It means we can say that this iodine is an oxidizing agent, right? So oxidizing agent is a species that reduces the molecule and is itself reduced. So iodine has reduced from oxidation state of 7 to oxidation state of 5, right? And here we're getting 2 products. So one of this is aldehyde and second of this is a ketone, right? So reaction is further worked up with acid, so we add some dilute acid in it. So The purpose of writing this hydronium ion is to, I mentioned that this process is carried out in presence of an acid, right? So the purpose of showing this molecule is that you can move the arrows in this direction or in that direction, doesn't matter. The important thing is that you have to show that we are breaking this carbon bond and we are forming carbon oxygen bond, right? So it doesn't matter which side you cleave the bond. You may cleave it on this way or you may cleave it on that way. So the mechanism remains unaffected by both of these manners. You may use any of these. So here we have some examples of this oxidative cleavage of diols. So suppose we have a diol here, MSE, and now we will see what will be the product of these reactions. Okay, so firstly we have to see the structure. Alright, so that's a diol and that's a diol and this is vicinal diol, fine. So what we will do, we will break this carbon-carbon bond from center. So we will break the bond between carbon number 2 and carbon number 3, right? And both of these will become carbonyl compound. So here we will have carbon-oxygen double bond, and similarly here we will have a carbon-oxygen double bond. So now we have to predict whether we will get an aldehyde or ketone or whatever. So you see that this carbon, it has a H and a methyl group. So this fragment will become an aldehyde, right? While this carbon has a hydrogen as well as methyl. So this will also become an aldehyde. So just by seeing the structure, you can predict that oxidation or oxidative cleavage of this diol will result in formation of two aldehydes, like this one. Right, so here we have this sodium periodate. You can see the sodium periodate it has oxygen, and there's 4 oxygens, while when it's converted into sodium IO3, so it has 3 oxygen. You can see that it has lost 1 oxygen. Right, this is loss of oxygen, and our substrate already had 2 oxygens, so product also have 2 oxygens each, 1 oxygen each with that. So where did the 1 oxygen that is lost by this NaIO4, where is that? So this is in the form of water, right? So this is justifying that we have got NaIO3 along with water, right? Similarly, we have another structure, and we now want to predict what will be the product of this reaction. Again, we have to break the bond between these two diols. So once we break the bond, we will convert this oxygen carbon single bond into carbon oxygen double bond. So we'll get a carbonyl compound here and a carbonyl compound here. So just see this carbon, so it has methyl group here and methyl group here. So this fragment will form a ketone, while this carbon, it has hydrogen here and a methyl here. So this will form an aldehyde. So you can see the product here. We have a ketone and we have an aldehyde. Right, let's take another example. So we have a diol here. You can see that. So this is the diol, 2-hydroxy on the adjacent carbons. So we have to break the bond from center. Okay, just cleave the bond from center, from here, and what we get, we have to convert this carbon oxygen single bond into double bond, and similarly this is also converted into a double bond. You can see on one side of this carbon we have a benzene ring and a hydrogen. So this carbon, that will be converted into an aldehyde, that will be benzaldehyde. While this carbon, it has a methyl here and an ethyl here, so this will be converted into a ketone. So this product, this reactant, will result in formation of benzaldehyde and a ketone. Right, so here we have another example. So we have a cyclohexane diol, right, and this is a cis diol because both of these hydroxyls are on the same side, on above side, right? So we have to cleave this one from the center, and we have to convert both of these carbon oxygen bonds into carbonyl compounds here. Okay, so we have a hydrogen here and a carbon here, so this will convert it into aldehyde, and this carbon also has a hydrogen here which is not being shown and a carbon here, so this will also convert it into aldehyde. So So when we carry out the oxidative cleavage, we break the carbon-carbon bond and form two carbon-oxygen bonds. So what happens that we get two aldehydes which are attached here. Okay, so these are further few more examples you may see. So here we have a simple diol, and you may see that after breaking we get two ketones here. Similarly, okay, if we break from here, so this carbon has a hydrogen and a methyl group, so that's form an aldehyde, and that will form, we say that we have a ethyl group here and a hydrogen here, so this will also form an aldehyde, right? So this molecule, once cleaved, will result in formation of two aldehydes, and both aldehydes will be different. Now we have this molecule, right? So we have a diol here. This is glyceraldehyde basically, so this is a carbohydrate. So you have to break the bond from the center here and convert both of these into carbonyl compound, right? So in this specific case, since we have already this fragment here, so that will form formaldehyde by oxidation of this aldehyde group, and this group will form formic acid, and then we will form a formaldehyde here, right? So this fragment, this bond formation of carbon oxygen double bond will form a formaldehyde group. So this is the formaldehyde, right? This fragment in this specific condition, so this molecule is a bit different. So once you have a structure like that, so since we have an aldehyde group on the top, this aldehyde group will be converted into formic acid under these conditions, right? So this form formic acid. This molecule will again form a formic acid, right? So this central atom, this central carbon, will also be converted into formic acid, while this last carbon will be converted into formaldehyde, right? So one thing is important, that for example, if you have a system like an epoxide, so epoxides also undergo oxidative cleavage when we use hydrogen peroxide, right? So what we get is that we'll break this bond between carbon-carbon, right? And what we get an aldehyde from this side and aldehyde on that side. The reason being that this epoxide, firstly, in acidic conditions, and since we are also using water in the reaction medium, that gets converted into diol first, right? That's the trick. So we can use an epoxide, and since the oxidative cleavage requires presence of water as well, so what happens, this epoxide will undergo the ring opening and it will form a diol, right? So just assume that we have a hydroxyl here and a hydroxyl here, right? Just break the bond and we get an aldehyde here and an aldehyde here. So this is the aldehyde which has been shown here. Alright, so last example, we have a dihydroxyacetone, right? So this is acetone, and on each carbon we have a hydroxyl group, right? So what happens, that we have to break this bond, right? And just break this bond between carbonyl and this alcohol, and we will get this into formaldehyde. Then this carbonyl group will be converted into carbon dioxide in this specific condition, and the last alcohol, that's also converted into formaldehyde. So by cleavage of this molecule, by oxidative cleavage of dihydroxyacetone, we get two formaldehydes and a carbon dioxide, right? So you should be able to predict the product by just seeing the reaction, right? So we have now seen that we have used sodium periodate for the oxidative cleavage of diols. However, we can make use of lead tetraacetate as well. So lead tetraacetate works in almost the same manner as sodium periodate, right? So it also involves formation of a 5-member cyclic intermediate, which is shown here, right? That's an intermediate, and this is the mechanism. So lead acetate, firstly, that gets binds to this diol molecule, and we lose two acetate molecules, because during coordination of these hydroxyls with the lead acetate, we have to replace two of the acetates with these oxygens, right? So these oxygen form coordinate covalent bond with the lead acetate, and upon cleavage, you can say So you can see that this carbon bond is broken. So we are cleaving this bond from the center, and we are forming a carbon oxygen double bond here. And similarly, a carbon double bond oxygen is forming here. So in this specific case, since this carbon is both attached to R groups or alkyl groups, so this will form a ketone. Similarly, this carbon will also form a ketone here, right? So either you use sodium periodate or you use lead tetraacetate, both reactants work in the same manner, right? So now we will consider the oxidative cleavage of alkenes. Right, so oxidative cleavage of alkenes is generally classified into two groups: gentle cleavage or strong cleavage. Right, so gentle cleavage means that cleavage that takes place under milder conditions. Right, and when we carry out the gentle cleavage, we always yield aldehyde or ketones. Right, so gentle cleavage can be carried out either by means of ozonolysis or by means of Syn-dihydroxylation by the periodic acid. Right, so Syn-dihydroxylation is the same way by which we had converted the diols into aldehyde or ketones, right? So one thing you should know, that when we consider the gentle cleavage, gentle oxidative cleavage, it means that our product will be aldehyde or ketone, and we are using the reagents which are milder, which are not harsh. But the strong cleavage means that the aldehydes, the alkenes will be converted into carboxylic acids. We will not get aldehyde in this process. However, if we have internal carbon means a substituted carbon. So if the carbon is substituted and we get ketones, the ketones cannot be converted into carboxylic acids. Right, so this you should know, that gentle cleavage always yield either aldehydes or ketones. However, the strong cleavage yields carboxylic acids, and in case if a ketone is being formed, the ketone will not be converted into carboxylic acid by this method. Right, so at first glance this means it seems very silly, it seems very obnoxious to have more reactions for the same functional group conversion. Ultimately, we are converting the alkenes into carbonyl compounds. Why we are using the gentle or the strong cleavage method? The reason is that in synthetic organic chemistry, it often becomes necessary to target reactions of a single functional group into organic compound with multiple functional groups. Right? So sometimes you want a certain desired product. So you may prefer formation of carboxylic acid in certain reaction. So if you want to make carboxylic acid from alkene, you cannot go for gentle cleavage. Similarly, if you want to prepare aldehyde from an alkene, you cannot go for strong cleavage. You should know about the procedures which yield gentle cleavage or which yield the strong cleavage products. Right, so oxidative cleavage can occur by several different methods. It can be gentle or it can be strong, depending on the reaction conditions, and it also depends on the workup of the initial reaction product. Right, that's important, so we will discuss once we go in the detailed mechanisms. So cleavage can be strong or gentle, that depends on the reaction conditions, whether the reaction conditions are mild or not, and also on the workup of the initial product. Right, so we'll see about that in detail now. So this is just general representation. So we have an alkene here. Right, you can see this alkene, this carbon. So this carbon has two hydrogens here, so that will definitely form an aldehyde, and this has a hydrogen and a methyl, that's definitely form an aldehyde as well. So when we carry out the gentle oxidative cleavage, right, so whenever we carry out the gentle oxidative cleavage, it's always the reductive workup that we use. Right, so what we mean by reductive workup, we will go in more details further, but it's important to note, it's important to remember, whenever you go for the gentle cleavage, it's always the reductive workup that's used. So in gentle cleavage we get the aldehyde, so this will form the formaldehyde and this will form the acetaldehyde as well. Right, so now in case of the strong cleavage, when we use very strong reagents, very harsh reagents, then the workup is oxidative nature, right? So in oxidative workup or in strong cleavage, what we get carboxylic acids. So this carbon with 2 hydrogens, that will not form aldehyde, that will form carbon dioxide, right? So you may just imagine that the molecule that forms formaldehyde in gentle cleavage will result in formation of carbon dioxide, and the molecule that forms aldehyde in gentle cleavage will form carboxylic acid in the strong cleavage. However, if gentle cleavage results in formation of ketone will also be formed in strong cleavage, right? So इसका मतलब ये है कि अगर आपके जो प्रोडक्ट है, अगर फॉर्मल्डिहाइड बन रहा है जेंटल क्लीवेज में, तो स्ट्रॉन्ग क्लीवेज में वो प्रोडक्ट कार्बन डाइऑक्साइड होएगा. लेकिन अगर आपका जो प्रोडक्ट है वो कोई भी एल्डिहाइड बन रहा है जेंटल क्लीवेज में, देन स्ट्रॉन्ग क्लीवेज में वो फॉर्म करेगा कार्बोक्सिलिक एसिड. जेंटल क्लीवेज में अगर आपका कीटोन बन रहा है तो स्ट्रॉन्ग क्लीवेज में भी कीटोन ही बनेगा. सो दैट्स द डिफरेंस बिटवीन जेंटल क्लीवेज एंड स्ट्रॉन्ग क्लीवेज. Alright, so firstly we will consider the gentle cleavage. So we will start with Syn-dihydroxylation, and Syn-dihydroxylation followed by periodic acid treatment. Right, so this reaction is a two-step reaction sequence, right? So firstly what we do, we convert this alkene into Syn-dihydroxylated product, means we have to convert this alkene into a diol. Right, so firstly we can convert that alkene into diol, right? So the conditions are, you may see that conditions are cooled, you are not increasing the temperature, slightly basic, we are not using acidic conditions, and we may use KMnO4 or osmium tetroxide in presence of hydrogen peroxide. Right, so once we have carried out the dihydroxylation, we have converted the alkene into the diol, then next we oxidize this diol by means of periodic acid, means HiO4. Right, so let's see some example. So firstly understand what we mean by internal carbon. So this carbon, this is disubstituted, this carbon of alkene which is disubstituted, this is called internal carbon, right? Because it is eclipsed between two substituents. Right, since this is eclipsed between two substituents, that's why this is residing inside, so that's the internal carbon. While this carbon is exposed, it has a hydrogen on one side while carbon on the other side, so this side is exposed, so this is not external carbon. We say this carbon of the alkene is terminal. Right, so you can say that in case of alkenes, the carbon which is disubstituted is called internal carbon, and the carbon which is less substituted is called the external or the terminal carbon. Right, so always remember that in case of oxidative cleavage, the internal carbons, in case of general cleavage, the internal carbon will form the ketone while the terminal carbon will form aldehyde. So this carbon, since it's internal, that form a ketone, while this carbon will form an aldehyde. Right, so we have two options to carry out the general cleavage. Either we use cold potassium permanganate, KMnO4, right, and we have not shown potassium here because potassium is spectatorine here, and we have to maintain slightly basic conditions, so the pH is greater than 8, right? And then second step we oxidize with HiO4, right? So what we get an aldehyde. So this carbon was actually the terminal carbon, you would say, right? So this carbon which is the terminal carbon, that's forming the aldehyde, while this carbon which is the internal, that's forming the ketone. Right, so this is the general cleavage by means of Syn-dihydroxylation. So why we are calling Syn? Because the two hydroxyl groups that will be introduced, that will be added to the double bond, will be on the same side. Right, so in case if two same groups are on the same side of a carbon-carbon single bond, such groups are called Syn. Right, so since both of the hydroxyl groups are on the adjacent carbons and both of the hydroxyl groups are on the same side, so we say that these two hydroxyl groups are Syn to each other. Right, so next we have the gentle cleavage, and in gentle cleavage we are now using a different reagent, which is ozone. Right, so ozone is usually formed in the upper atmosphere and its formula is O3. It's a dipolar molecule actually. right? So it has been shown that when ozone reacts with alkenes, that results in cleavage of a carbon-carbon double bond, right? So previously we have broken the carbon-carbon single bonds, but here ozone has the ability to break the carbon-carbon double bond. So we can see that how it can break the carbon-carbon double bond. But just consider that the ozone is a scissor, right? And it cuts the double bond from the center and cuts the double bond to the half, and just add oxygen to both of these halves. So you get two carbonyl compounds. So if we cut this into half, so this is carbon oxygen double bond, you can say that's an aldehyde. Similarly, this half will also yield an aldehyde, right? So when we carry out the ozonolysis, ozonolysis means lysis or breaking by ozone, right? So first step is we treat the alkene with ozone, and the second step we will use zinc and some acid, right? So we'll see what happens next. Right, so what happens that we pass ozone through the alkene solution, right? The alkene solution is normally taken in methanol or in dichloromethane because ozone is soluble in these medium, right? So we take the alkene in methanol or in dichloromethane, right, and we pass ozone through it. So first what happens, the ozone adds to this alkene molecule and an intermediate which is called ozonide is formed. Right, so this ozonide is unstable molecule, and this ozonide actually rearranges itself, which is further reduced to carbonyl compound, right? So the breakage of bond between carbon and carbon and formation of carbon oxygen double bonds take place in this step. So let's see. Okay, so you can say that the ozonide, right? So this is rearranging, and you can see that so this oxygen will attack on this carbon, and this pi bond is attacking on this carbon, so we are forming this ozonide, right? And what happens that this ozonide is unstable. Why it's unstable, you can see that here we have oxygen-oxygen single bond, right? So whenever there is an oxygen-oxygen single bond, this is called peroxide, right? So this is peroxide, and oxygen-oxygen single bonds are highly unstable. So this molecule is unstable. This intermediate is unstable, so that's why that will break down further, right? So, and when it will cleave, we can say that we will cleave in such a way that this oxygen bond will cleave in this manner. So this oxygen will shift from carbon oxygen single bond to this carbon oxygen bond, and that will form a double bond here, right? Similarly, this bond will also be cleaved here, and we'll get a double bond here. So we'll get two carbonyl compounds here and here, right? So now the next step, why we mentioned zinc. So in the second step we add zinc because zinc has to pick up the extra oxygen from that. So just see this extra oxygen, right? So this extra oxygen will be picked up by this zinc atom. So instead of zinc, you can make use of dimethyl sulfide, right? So when we use zinc or when we use dimethyl sulfide, this reaction is called the reductive workup, right? And when we carry out reductive workup, we always yield aldehyde or ketone, right? The reaction stops at this position. However, in case if you don't use zinc or dimethyl sulfide, instead you use hydrogen peroxide, right? So when you use hydrogen peroxide, this workup is called oxidative workup. So in case of oxidative workup, what we yield is that the carbonyl compounds, if that's an aldehyde, that will be converted into carboxylic acid, right? Ketone will remain as such. Ketone will not be converted into carboxylic acid. However, if you have an aldehyde, if you have terminal carbon, right, the terminal carbon will be converted into carboxylic acid, right? So although ozonolysis is a gentle oxidative mechanism, however, that can be considered as a strong oxidative cleavage if you use the oxidative workup. So if you are using the reductive workup, so reductive workup will be gentle, and we will get the aldehyde or ketone. However, if you are considering the Oxidative workup means that you are using hydrogen peroxide, then in that case the terminal carbon, the less substituted carbons, will be converted into carboxylic acids. So let's see for some example. So again, we are taking the same substrate for better clarity. So here we have a methyl cyclohexene, right? You can see this carbon is internal. Why it's internal? Because it's disubstituted here. While this carbon, that's terminal. So terminal carbon, in case of gentle cleavage, result in formation of what, an aldehyde, but in case of strong cleavage, that will be converted into carboxylic acid. While internal carbon, that will form ketone, right? That form ketone in the gentle cleavage. It will also form the ketone in strong cleavage. You can say that if you use zinc, that is the gentle cleavage, right? But when you use hydrogen peroxide, that's a strong cleavage. So this is a strong cleavage. The conditions we are using are, you would say that KMNO4, and we are using the KMNO4 in warm state. So this is a harsh state conditions, right? So that's the strong conditions. Okay, now we will consider the oxidative cleavage for alkynes. Wow. Okay, so if we have a triple bond and we have to break the triple bond, we have to break the 3 bonds, then we can do so by using ozone again, right? So when we use ozone, what we get is that we will break the 3 bonds, mean the triple bond, and we will get 2 carboxylic acids, right? So here we will not get any aldehyde, or we will not get any ketone. So whenever you are getting out the oxidative cleavage of alkynes, what we get is only the carboxylic acids here. So you can see that we have broken the bond. Just consider that we are using a scissor and just cut this triple bond into center, right, and add 2 oxygens to it. So one oxygen will be in the form of carbonyl compound, carbonyl group, and other will be in the form of OH, right? So here you can see that. So we cut this between carbon 2 and 3, and we have made a double bond with oxygen and single bond with OH. So we get 2 carboxylic acids here. Okay, so another example, suppose we have phenylacetylene, and we have to carry out the oxidative cleavage. So what will be the product? Just consider that we are using a scissor and we are cutting these 2 carbons from the center, right? So just convert both of these into carboxylic acid. So here we'll get a benzoic acid, that's benzoic acid, and this carbon from the formic acid. So this is the formic acid here, right? So this is the simple alkynes. So if you have to carry out the oxidative cleavage of alkynes, the only option is to use ozone, right? So we will consider now the oxidative cleavage of ketones, right? The oxidative cleavage of open chain ketones is not a preparative method, right? We get a number of products. So we do not normally carry out the oxidative cleavage of open chain ketones. However, if you have a cyclic ketone and that is symmetrical, right? So both things are important for that. So you must have a cyclic ketone, and that cyclic ketone must be symmetrical. So if these 2 conditions are met, we can carry out the oxidative cleavage of the cyclic ketone. For example, consider this cyclohexanone. So this is a cyclic ketone, and you can see this is symmetrical. If you cut the molecule from the center, from here, so both of these halves will be exactly the same. So what we do is that we carry out the oxidative cleavage of cyclohexanone, and for that purpose we use nitric acid in presence of vanadium pentoxide. So you have to use nitric acid, and you have to use vanadium pentoxide, V2O5 with that. So what happens that we will break this bond from one side and convert both the ends into carboxylic acid, right? So you just cleave the carbon-carbon bond from here, right? So we break the carbon-carbon bond from here, and right, so convert both of these corners, both of these end in the carboxylic acid. So what we get, reactant or cyclohexanone, while the product will be adipic acid. So we'll get 2 carboxylic acids at both ends, right? Okay, so along with certain cyclic ketone which is symmetrical, any ketone which have alpha hydrogen can be oxidized, but we have to oxidize it by prolonged heating with some strong oxidizing agent. right? So if you do not do the prolonged heating thing, you cannot oxidize it further, right? So if you have a ketone and if the ketone has alpha hydrogen, that it can be oxidized, but you have to do the prolonged heating, and you have to do the prolonged heating with strong oxidizing agent like potassium dichromate or with nitric acid in presence of vanadium pentoxide, right? So why alpha hydrogen is important? Because you know that alpha hydrogen, if a ketone has alpha hydrogen, that it can be converted into enol form, right? So if you are using acidic conditions or basic conditions, then in both of these conditions we can get an enol form, right? Just consider this ketone, it has alpha hydrogen on this side or alpha hydrogen on that side, so we can form enol on both sides. So it can form enol on this side or it can form enol on that side. Since molecule is symmetrical, doesn't matter, right? So here we have the enol form, so we have carbon-carbon double bond, right? So since we have a carbon-carbon double bond, it will be oxidized just like the strong cleavage of alkene. Remember the strong cleavage of alkene, so it will break from the center and both of these will be converted into carboxylic acids, right? So we can convert cyclic ketones if they are symmetrical, or if we have a open chain ketone with alpha hydrogen, then we can carry out the oxidation cleavage, oxidative cleavage of these ketones. But what we have to do, we have to use the vigorous conditions, we have to use strong harsh conditions, and in that case we will get the carboxylic acids, we will not get any ketone here, right? So that's another. So we can use vanadium pentoxide in presence of nitric acid, so we will get adipic acid. Also, instead of using this vanadium pentoxide with nitric acid, we can use sodium oxychloride as well, right? So the solvent in that case will be an alcohol, for example ethanol, and the medium should have sulfur dioxide, right? So under these conditions, if you have a cyclic ketone and you have sodium oxychloride, which is actually bleach, and this alcohol, for example we have mentioned here ethanol in presence of sulfur dioxide gas, then in these conditions so we'll get the cleavage of carbon-carbon double bond here, because that will be converted firstly into enol form, right? So consider that this ketone is firstly converted into enol form. If we have a double bond here, just cleave the double bond from here. So convert one of the carbonyl compound into ester, right? This carbonyl, this will be converted into ester, while this carbon will be converted into oxime, right? So here we have an oxime here, you can see that, right? So this is oximino carboxylate, or you can say that we have a carboxylic ester and an oxime on one end, right? So it depends on, so if you are going for an ester with oximino carboxylic ester, right? So if you are going for this molecule, then you have to use bleach in presence of alcohol. However, if you are just going for the dicarboxylic acid, you want carboxylic acid here and you want carboxylic acid here, then you have to go for nitric acid in presence of vanadium pentoxide. Okay, now we have another substrate. Suppose we have cyclic 1,3-diketones like that, right? So what we do, again, these cyclic compounds normally exist in the form of enol. So we have a carbon double bond here. So what we do, we just carry out the oxidation with sodium periodate, so it will just undergo oxidation just like the alkenes. So just gentle oxidative cleavage of alkenes. So we will break this bond like that, right? So we have a hydroxyl group here, and since that's an enol form that can exist in the form of ketone, so what we'll get, so we under these conditions, if we have 1,3 diketones, what happens that this central oxygen carbon bond will be converted into oxygen. Alright, so this oxygen will be lost, and what we get, we will get, sorry, that will be formed in the form of carbon dioxide. So that's an error, right? There's an error, actually that's carbon dioxide here, you can correct it here. So we will get carbon dioxide from the center, so this carbon dioxide will be lost, and both of these carbonyl compounds will be converted into carboxylic acid, right? So the oxidative cleavage pattern for cyclic 1,3 diketones is a bit different, because in this specific case we ultimately lose one carbon. So you're starting with 6-membered cyclic system and you end up with 5-membered a 5-carbon dicarboxylic acid. So if you count 1, 2, 3, 4, 5, so we have 5 carbons and 2 carboxylic acids here, and one of the carbon has been lost as carbon dioxide. So hope you have understood about this lecture. So you have to solve this quiz. So you have to predict what's missing in here. So in case of the product is missing, just predict the product, and in case the reactant is missing, by seeing this product you have to predict what was the missing reagent. I hope you have understood this lecture. Thank you.